This is Kettering University.
Thanks for coming to our talk today. So I have almost a 180-degree angle to deal with here. So I'll try to scan you all, make sure everyone is feeling included. Thank you. Okay, as was mentioned, I'm going to talk about non-destructive evaluation from materials science and from an electrical engineering perspective with a bit of a physics background, okay? So before I do that, I just want to tell you a little bit about Iowa State. And it's a very different school than this one here. So just bear with me while I give you a bit of an introduction on that. Just in case you didn't know, this is where Iowa is. It's not too far from here, so hopefully you do know. Anyway, this is cardinal and gold are the school colors, which is why we colored it there. So we're a little bit north of Des Moines, which is the state capital. It's the first land-grant university. We might smile. Michigan State also claimed to be the same thing. They were the first to actually issue degrees, but we got our status sooner, so we kind of compete over that. So basically, engineering and agriculture are big. 35,000 students, so imagine it's a lot different than here. And we've grown by about 10,000 in the last 6 or 7 years. So there's just a lot of people around. Lots and lots of research going on. In our department, we have about $12 million of research spending every year. And we have 7 academic colleges, engineering being listed first, of course. This water tower is by my building. I'm in materials engineering right here. This is a historical landmark on our campus. So in engineering, we have 10 graduate programs and lots of interdepartmental engineering programs as well. We have about 8,500 undergrads right now and 1,000 grad students in the college. And just in case you're thinking of going on for grad school somewhere else, these are the different things that are available. These 9 up there, the various disciplines. We also have a wind energy PhD program, which is pretty interesting. It's a unique offering in the United States. Iowa is the second largest producer of wind energy by state in the United States, so that's why we focus on that. And if you're interested, you could talk to me about how you would apply and get in. I know this school has this interesting co-op thing, so a lot of you are focused in getting into industry, and that's a really nice structure, I think. But grad school is fun as well. Our department, I'm primarily in materials engineering now, although I have partially appointment in EE, and we have a Nobel Prize winner from a few years ago. It's very nice. Some of our areas of research include this one where I am down here. Also computational materials, some other things. We focus on some characterization as well. This here is related to the field of NDE. I don't know if anyone has ever heard of this incident or even recognized what it is, so I'll tell you. This is an aircraft engine, and this is a disk from the neighboring engine that fragmented. It was on the ground. I think it was at LAX, and I don't remember when, maybe 20 or more years ago. But this piece of the engine, as it was rotating, fractured, and it went through the fuselage of the aircraft and embedded itself in the casing of the opposite engine. So it's a very high energy event. And this kind of thing is something that non-destructive evaluation is trying to prevent, okay? If we can look at a material like this fan disk from an engine and find any defects in there, like a crack or something even smaller that gives rise to a crack, if we can find that, we can maybe stop this kind of incident happening. This one, I don't think anyone was injured because it was on the ground, but in air, obviously, this would be a major traumatic event. Just a little bit about the EE department. We're going through the intro here. This one's a big department in the college, about 1,600 undergrads, lots of activity going on. And not everybody knows, but in graduate school, you usually get a sponsorship so that you have either a research or a teaching assistantship or other kinds of sponsorship. So you don't have to pay your tuition and you get a stipend as well. Some of the areas that department's interested in, EE, bioengineering, communications, power, I understand, is something that you have courses in here as well, and we have power emphasis as well, non-destructive evaluation. And then computer security is something that, that our department is well known for as well. So what brought me to Iowa State originally was this Center for Non-Destructive Evaluation. And okay, if you're not familiar with the concept of NDE, then think about medical kind of inspection, if you like. If you have something wrong with you, a doctor has a suite of different characterization techniques that he or she can draw on. So think of X-rays, ultrasound, and any others, visual inspection even. These also are used in engineering contexts. So the research that we have here is one of the biggest collections of university-based tools in this area. Ultrasonic testing of structural materials. Eddy current, that's an electromagnetic testing technique. X-rays, thermal waves, microwaves, terahertz, capacitive, and dye-penetrant is a visual inspection technique. So we do all of these things under one roof, essentially, which is unique in the United States for a university. And what you find is in a lot of industries, they will have an NDE department or division. So in manufacturing, processing, materials development, in the Air Force, in other industries where they're looking at structures that operate over time, they will have an emphasis on NDE somewhere. So we also have an online grad certificate that can be taken by people in industry in particular. I had some involvement in setting that up. So just one day in the future, you might find that it's useful for you to know about that. Okay, that's the background. So if you have questions, you can ask me afterwards. So more focusing down on what topic I'd like to talk about today. I have various research interests. These kind of change as time goes by, but primarily electromagnetic NDE for materials characterization. And today I'm going to give you two examples of areas I've worked in on that topic. Related to that, I'm interested in polymer aging, which is how I've really got connected with Professor Hizroglu here, and also polymer matrix composites design and characterization. Okay, so today, this one is the one I'm going to focus on with two examples. Okay, so I'm going to write something on the board now, and I might ask you a question or two. So I'm going to have a couple of emphasis areas. One is on metals, and the other is on polymers, okay? Now, if we want to discover something about these different materials, we have to choose the right way of measuring their properties, okay? So in the case of metals, what electrical properties do we know about a metal? Tell me, yeah.
Conductivity.
Okay, thank you. I'm going to give that the symbol sigma here. Is that okay with everyone? All right, and so that could be the inverse of resistivity, obviously. So we've covered those two. What else might there be about a metal that, yep. Okay, so permeability might be another one. So these two are what I'm going to talk about today, actually. What about in case of polymers, though? Typically, we wouldn't expect to see these guys in a polymer. So,
Insulation.
Okay, it's an insulating material. So what material property is related to that? Resistivity, it's very small. It appears as, let me see if I can focus. What is the primary property of a dielectric? You know, what is that? Sorry? Permittivity. Okay, great. So permittivity, I'm going to give the symbol epsilon here. And then the conductivity comes in as a kind of part of this, as an imaginary component of that. So yeah, absolutely. Okay, great. So these two, I'm going to give some examples about how to characterize materials by measuring these properties. Okay, so the first method I'm going to talk about is a 4-point probe for measuring metal character. Anybody familiar with this? I don't know if you do any semiconductor characterization. It's often used to look at surface resistivity. So the idea with a 4-point probe is pretty simple. You put a current into your test piece. This is the test piece, through one point, and it travels through, and it goes out through another point. And we use 4 points because there's something called contact resistance that happens here that we can't quantify. So we use these two as kind of the measuring points, and we measure the potential difference between those two pickup points. And that voltage depends on the structure of the material and its conductivity and so on. So you can actually determine something about the material by passing a current through here and measuring the voltage across there. Okay, does that seem reasonable to everybody? Okay, good. All right, normally we do this in a kind of quasi-DC type way, but if you use a broadband approach, so you change your frequency, you can actually get more information out of the material. And if we do that, we then have a little pickup loop here we have to worry about. So we just try and make that as small as possible because this will give us some contribution to our measurement, but it doesn't tell us anything about the material. Okay, so that's something we want to minimize. So I just mentioned that there. Okay, so we're going to measure potential drop across these 2 points and find something out about the material. So where are these used at the moment? As I mentioned, in the semiconductor industry, surface resistivity is typically characterized using a probe like this. Also, on much larger scale geophysical applications, and for archaeology, you can get a probe this big. You can walk around a field and you can map its resistivity and find buried information in the soil underneath. We also use it to measure conductivity, in particular of ferromagnetic materials, and there's a reason eddy current NDE fails at that. Okay, so we have 4 points. What can we do with those? These red dots here I'm using to indicate where the current goes in and out of the material. We're looking down on the surface now. And so maybe it's being injected here and it's extracted there. And this is what the electric field distribution looks like if you look down on there. So it's more dense near the points, and it spreads out as you get further away. So if you want to measure some property of the material, you can put your pickup points down any way you like, actually. So one common way of making a probe like this is to make a collinear probe. So you have your 4 points in a straight line, and these are now the pickup points. And the potential difference that you'll measure depends on where those points are and then the density of the current or the electric field distribution in between them. Now, if you wanted, you could move your pickup points somewhere else. And sometimes when you're making a probe, it's useful to be able to change its shape for practical reasons. Now, this one here, though, we're choosing a different kind of organization of the pins. In this case, normally the signal would be 0, right, between these 2 blue points. And so that's useful if you're looking for some kind of change in the material. So maybe there's a crack or an inhomogeneity, some kind of inclusion that has different properties than the surroundings, and then that is a useful configuration. When it becomes unbalanced, you can detect that easily. But for material property measurements, we would usually use something that's more like this in an unbalanced kind of way. Okay, so that voltage, and this is all fairly simple sort of in terms of its physics, That voltage that we're measuring then is determined by how you arrange your probe points. It's also determined by parameters of the test piece, its conductivity, permeability, and also geometry, and also presence of defects and so on. So in terms of geometry, we could think of a flat plate type geometry. We could think of cylinders. And in fact, one of the examples I have is looking at the properties of crankshafts that are hardened for improving their resistance to wear. So if we properly interpret this measured signal, then we can find out something about the test piece. As I mentioned before, in sort of historically speaking, this probe has been used with mostly a DC or a quasi-DC type of current, but practically we prefer AC because it avoids resistive heating in the part. Now, often people use a low frequency AC current, but they interpret it using a DC theory, and usually that's okay, as long as you're in the right part of the theoretical regime. But what we did was we actually took that technology, we kind of expanded it in terms of using higher frequencies, because we can get more information that way. So I'm going to enter into a little bit of physics-based theory for a little while. So who likes equations here? Good, yeah. I like this place. I get this real sense that you have this good underpinning in terms of really wanting to know what's going on. Okay, so you're not scared of theory. That's good. All right, so let's say we have our 4-point probe, and we want to know in general how it behaves. So I'm going to just arbitrarily put down my injection points and my pickup points as in this diagram here. So these rho values is not resistivity, it's just the distance between these different points. Okay, so it's just a spatial dimension. So what we want to do if we're designing a probe is figure out how can we calculate V, our pickup value, based on all these different things about the system. So this potential difference is the voltage at position 1 minus that at position 2, which are given by the blue dots there. Now, if you have a planar surface with a conductivity sigma, it turns out you can analyze this system and you find out this relationship. So this potential drop is simply proportional to the current divided by 2 pi times sigma. And you have this function that depends on all those different distances between the points. Okay? Now, if we think about this slowly, if you put in a current here, it has associated with it an electric field distribution. Okay? And now the potential difference between that point and another one is related to the distance between them. Okay, so that's what's going on here. This function is talking about the potential here related to Q2. One other point I want to make here, if you work just at low frequency, then it turns out that this value is just one number. It's a real number. Okay, pretty simple. If you work at AC, you find out it turns into a complex number. So there's a quadrature component appears as well. We'll see what that means by an example here. Okay, now this is a plot of taking one of those 4-point probes and putting it down on a copper rod. Okay, so we're putting 4 points along the side of a copper rod. It's 11 millimeters in diameter. What we find as we change frequency, so down here is 1 hertz. As we increase that, this is 10 kilohertz up here. This is what we call the DC regime, the quasi-DC, okay? Because everything is just one number. The geometry doesn't matter, okay, until you get up to higher frequency. So this is the DC limit. This was what would be measured at low frequency. These red crosses are actually experimental data, and the blue line is our theory, okay? Now, when I was an undergrad or even a grad student, I used to get, and I still do, excited about this sort of thing. You know, here's an experimental measurement. And here's some mathematics, thanks be to Maxwell, that we can predict exactly what we get when we go in the lab and we do a calculation. And they are somewhat separate in a sense. And then look at that, it's beautiful accuracy here. Now, that's the real part. If we look at the imaginary part, we find that that goes to 0 at low frequency, okay? So that's why we can get simply one number of potential drop when we are looking at low frequency. As it goes up, though, the imaginary part starts to creep in, and we'll see a little bit of why that happens in a moment. All right, so just going back a little bit to what's happening when, let's consider just one current injection point on our surface and one pickup point. If you have an infinitely deep material, we call that a half space, then the potential actually just radiates out as though it's on the surface of a sphere. So it decays away as 1 over the distance from the injection point. Now, in some cases, practically, that will actually be a good formula, because if you have a particularly thick material, and if your probe pins are quite close together, then actually this formula will be valid, and it's a very simple calculation to determine potential drop. And that's what that would look like. You have potential drop equal to the current divided by something, 2 pi sigma, and you have those distances between the different 4 points of the probe. So what that means then, you can play around with these distances now. So the distances between the different pins, you put in some values there. And if you have a collinear probe, which would be like this, with an equal separation between those, which I've called S here. So if those distances are all the same, then you can express your conductivity in this really simple formula. You know, it's a back of the envelope type of formula. We could even do that in our head. So this is the distance, this is the potential drop, the current, and you've got the conductivity very simply like that. There's not many testing approaches that are as simple as this. One thing to notice here is even if you have a magnetic material, it doesn't feature in this equation, which is why we can use this to measure conductivity of ferromagnetic materials quite easily. So that's the DC regime. If you take it up to higher frequency, though, you get a much more complicated formula for the dependence of that potential drop. So you have to go through lots of Maxwell equation type analysis to get this kind of equation here. And what's new is that we have this factor K in particular that is related to several things about the material and to the frequency. So this is like a kind of, it's a loss factor really. We're used to using K for a wave number. This is like the complex lossy part of that, because the metal is essentially a lossy conductor. So we have the imaginary unit here, then we have the angular frequency, we have the permeability of the material, and we have its conductivity as well. And so that's why as you go up to higher frequency and that curve changes, we can actually extract permeability information about the material as well. Okay, so you can have a function like this, and that's how we could get that nice fit between experiment and theory. If you want to know some different formulas for different shapes of materials, we worked out quite a lot of those. So the shapes are here. So if you have a half space, that's kind of the simplest case. You know, it's very deep kind of plate would approximate that. If you have a thinner plate, you have a different kind of formula. If you have a coated half space, you have a different formula again. And if we were to look at a cylinder, which has a nice application in the auto industry, In fact, there's still no really good non-destructive way to measure the depth of a hardened layer on a crankshaft, which people would like to have. Then we would have different formulas as well, which are actually pretty difficult to work out. So, okay, equations are good. Applications, let's look at a couple of examples. I did a comparison between some standard methods of measuring conductivity and then the potential difference approach. And these ones are based on using an induction coil. So I'm holding this thing. Let's pretend it's got a coil at the end. You put it down near a metal, and the impedance changes because of eddy currents that are generated in the metal. Now, that's a standard way of measuring conductivity. This is a commercial instrument for doing that. And this is a system we put together in our lab, so it's a bit more controlled. And then the AC system. It's actually more difficult to characterize a coil setup than it is to characterize a 4-point setup. The 4 points are just a simpler probe. You know, a coil, you have to worry about, you know, how many windings there are and the fact they wobble a bit, things like this. What it means, the bottom line is we can get better accuracy using the 4-point probe. So this is the percentage uncertainty in our measurement. I'm actually here in Michigan to go to a meeting about measurement science, and we care about how accurately we can measure things. So in this example, our commercial instrument, when you get in terms of measuring conductivity of a steel, it has really poor accuracy. It's about 40% wrong, okay? So we're not impressed with that one. 2% is all right. That's on a non-magnetic material. The eddy current system we have in our lab does fine. But then if you really want to get down to maybe understanding the difference between some different alloys that have similar composition, it's good to have you know, as much accuracy as you can, and our system did well with that. The other point about this is it's the only one that can measure the magnetic property of the material compared to those other eddy current methods. So that was a bonus. Okay, so that was on some plates that we measured. This other example is to do with surface hardened steel, which, as you know, is relevant in the auto industry and in many others. So what's done is, I was seeing someone's induction coil in a lab. You can either surface treat the material with an induction coil or with a carburizing process, for example. And this shows the hardness profile of those steel rods. So this one is surface hardened to about 1,000 microns, and this one has a thicker layer of hardening. But we sort of lack a good non-destructive way of measuring this. Does anybody know how these were measured? Do you have any experience with hardness measuring? Or okay, these particular ones, you have to slice your rod and you polish it, and then you take a little tiny indenter and you measure the size of the dent that you can make with your indenter. Okay, so the bigger the dent you can make, then the less hard it is, and you have to do all those correlations. So it's a long and tedious process. So we want to replace that with a simple non-destructive measurement. So we took our 4-point probe and we did some measurements on these materials, a couple different steels. And so what we found then is that these two types were hardened in different ways. This is essentially our 4-point probe measurement, and this is the midpoint of the destructively measured hardness. And we can get a correlation between the two. So there is a potential that we could replace that long-winded analysis with a quick NDE measurement. And this is another application. It's a helicopter rotor gear. These also are surface hardened for the same reason. We don't want them to wear out quickly. And so this here is where the 4 points are in this version of our prototype probe. So it's another application is the depth of hardness in those gear systems. There was a particular company who came to us, so having trouble with these things fracturing, and they particularly wanted us to develop this method for them. So maybe that's something new for you, this 4-point probe technology. We can precisely measure conductivity, can also measure permeability if we use higher frequencies. We can characterize the depth of hardening, and I didn't talk about, we can size cracks as well using this. These are just a few people who helped out with this work in the past. So that was my first part here. I'm going to talk slightly shorter now about some polymers testing work. So again, non-destructive evaluation is motivated by several things. One is safety, as we can see here. This is the kind of thing we want to avoid. This was a fatal crash in 1996. The conclusion was it was a short circuit from damaged wiring that caused this, this catastrophe. This is an example of some starting to fail wiring insulation, and what happens then is electrical engineers, you get shorts between the two wires, and it could cause a fire. So now we're not dealing with metals as such, we're dealing with something that this is the parameter, the permittivity that we want to probe. So how can we do that? Degradation of wiring insulation, it results in changing this property of the polymer. It's often a polymer these days. So if we change that dielectric property, we can measure that if we use a capacitor. Okay? So we're all familiar with the parallel plate capacitor, I hope, and you have a dielectric between there, it changes the capacitance. So if you have a wire whose polymer properties are changing, you can measure that through a change in capacitance as well. So this is the configuration we're all used to. Here's a dielectric between a couple capacitor plates. You can change that configuration to be more convenient if you want to. And for example, this is what we call a fringing field capacitor. So we've taken our plates, we've opened them up, and now we could use that as a surface sensor on a material. Okay? So we have a positively charged electrode, a negatively charged one. The electric field is kind of forced into the material, and we can find out something about it. So in this case, we have the simple formula. Capacitance is permittivity times the area of the electrode times the distance between them. Over here, we're going to have some more sort of complicated function of the geometry. Okay, we can't simply write that down. It's a little more involved. So where does permittivity come from? Just a little bit of material science here. There are several mechanisms that contribute to the value of permittivity in a material. One that all materials have is the top one, this either electronic or atomic polarization. So you apply an electric field to an atom, the positive and the negative charges separate and cause a dipole. Okay? So that gives us one contribution. Same thing could happen in an ionic system. You have positive and negative charges, you apply electric field, and there's a displacement, gives rise to a polarization. This one's a bit different, and it's more applicable to polymer systems. So in a polymer, you have long chains, you have side groups, where there may be a permanent dipole in there. And they may be pretty much randomly oriented if you have no external field. If you apply an electric field, they're going to try to line up a little with the applied field. And so this mechanism here exists in fluids, dipolar fluids like water, for example, or in polymers as well. And there's one other mechanism, but we'll leave that for another time. Okay, so the idea here is if you apply an electric field to a material and it responds in a certain way, then if it's damaged, it's going to respond differently, and you can detect that by measuring capacitance. Okay, so that's the idea. So going back to those mechanisms we just talked about, this top line is the permittivity as a function of frequency, showing what happens when you go above and below those different mechanisms we talked about. So again, in this case, frequency information tells us more about the material. So if we change frequency rather than doing it at fixed frequency, we can determine more about the material. And this is the range that I typically work in for sensors that can be used in the field. It's a typical LCR meter type range of frequencies. And what you see is this is only a schematic, but this is the roughly right range for looking at those polymer polarization mechanisms, the dipolar mechanism. So just to convince you, this is what permittivity looks like for H2O. The dark line is more or less, it's 273 Kelvin, so there's a temperature dependence is shown here as well. But as you see, the permittivity in relative terms of water is pretty high. It's over 80, that temperature. So water is a very polarizable fluid, actually, and this is why microwaves work. So this is about the microwave frequency, and you can put a lot of energy as heat into water at about the frequency of microwaves. Okay, so let's just get back to the wiring insulation thing. Here's Faraday's transformer, not insulated with a polymer. Just a very brief history. 1900s, polymers started to be used. These days, we're interested in modifying those using nanoparticles, so kind of an interesting area of research. But the topic today is how do we detect changes in the polymer before it becomes as significant as that. So a brief history of the use of polymers, particularly in aircraft insulation. We did this work for NASA and for Boeing. And Boeing were particularly interested in the use of nylon as an insulation material. And these different aircraft, 707, 727, 737, DC-8, back in around the 70s, this was commonly used in those aircraft. So that was our motivation. What does nylon look like? It has a repeating unit, which is between those brackets there. So what you can imagine is some of those side groups might be polarizable. They can move under the application of an electric field. And this is what the spectrum of nylon looks like as a permittivity measurement. As you can see, it changes as a function of frequency. The reasons for that is that material response is slowing down. It's finding it hard to keep up with that applied field change. And then the imaginary part has a peak in it corresponding to the drop here. So there's a lot of detail in there that I won't try to go into right now. But anyway, what did we do? We took a bunch of nylon samples and we aged them in various chemicals. And Boeing were worried about these kinds of things. What if the water gets onto the insulation material? Does that damage it? In fact, nylon attracts a lot of water, so it does have an effect. What about cleaning fluid or alcohol or, isopropyl for other kinds of cleaning? Deicer, jet fuel, hydraulic fluid. What happens to the insulating properties of the material if it comes into contact with these things? So we set out to investigate that. I just want to highlight these 4 are water-based, and these 2 are not. So that leads to some different behaviors later on. Okay, so we prepared a few samples. They're basically smooth, clean sheets. We actually heated them in advance to remove any moisture that might be present before we started. And then we immersed them in these fluids for a couple weeks. Okay, so here's a nice simple measurement that you can do without a lot of equipment. How does the mass change when you've immersed these samples in these different fluids? So let's have a look at that. Let's pick water first, which is the green one. So in distilled water, you see the mass increases up to a couple days, and then it's pretty much stable after that. But it's obviously taken in water molecules into the system. The black line, the cleaning fluid, follows a very similar pattern. The blue one, isopropyl alcohol, there's some interaction going on that means there's a greater mass gain for that one than the others. Deicer, still quite a gain, but it's slower, it takes longer. And then the other two, these are hydrocarbons. They are not water-based. Hardly anything happens at all, okay? So actually this measurement gave us a real clue as to what we might see in the electrical properties of the material as well. So that was the next thing to do. So this is our parallel plate capacitor right here. We can put our sheet-like samples in between those capacitor plates, and then we use the LCR meter to measure capacitance. So as we do that, these are the same colors as before, I think. This is underneath there is the pristine material that we did nothing to at all. And as you can see, there's hardly any change when you put them into the hydrocarbon-based fluids, jet fuel and hydronic fluid. But with those others, there's quite a big change in the permittivity when you've immersed them in water-based fluids. So that result gave us sort of some hope that if we developed a sensor to clamp onto a wire, we might be able to tell if it was degraded in some way by a chemical. And so this clamp was developed. The electrode area actually looks like this. So interdigital electrodes in this kind of way that you would lie the wire along here, and you clamp down on it, you take some measurements. And this is the result that we got for those different fluids here. On a typical aircraft wire with a nylon coating, we see that we can get some distinction between those different ways it was degraded. And down here, we kind of compare that with what we got on the nylon sheets. And we don't expect them to track perfectly for various reasons, but they do correlate pretty well. Okay, so in conclusion, we were able to show that nylon 6 aging is distinguished according to the polarity of the fluids that you put it in, either water-based or hydrocarbon-based. And in addition to that, our clamp capacitor shows that it's promising, I think, for detecting degradation through changing permittivity of the material. Okay, so last slide. So the message I'd like to leave you with is, if we couple together material science understanding and then understanding or development of sensing technologies, in this case electrical ones, we can find out about fundamentals of materials behavior. We can find out if they have good integrity, if they have the properties that we want. And we do this because we're interested in it, for one thing. We do it because it improves safety in structures. And we can improve manufacturing processes as well. And we can reduce costs. So all of those things are motivations for doing what we do. Okay, so thanks for your time. It was nice to meet you all.